Well, welcome everyone officially. My name is Angie Furman, and I am the River Training Center Coordinator for River Management Society. And I just want to welcome everyone to our Hydropower Insights webinar series. And this is a series that's building on the foundation that we started with the Hydropower Licensing Toolkit. And I'm going to put a link to that in the chat so you can check that out. The Hydropower Licensing 101 Toolkit was published last year by River Management Society, the National Park Service, and the Hydropower Reform Coalition. And so to build on this tool, we've designed this 4-part series where we're going to be addressing the gaps in available resources for hydropower practitioners and seeking an understanding of different aspects of hydropower projects and the licensing process. So again, welcome everyone. My name is Angie Furman again, and I'm going to be kind of helping out behind the scenes today. I'm going to be helping monitor the chat. And just a few reminders before we get going. We've got some great presenters today. We've got Kevin Lewis and Dave Steindorf. They're going to be talking to us today about the different types of projects, the key components, some common operation scenarios, and really just how hydropower projects generate and deliver power. So kind of this background, this does relate to a couple of the core competency areas in this hydropower licensing toolkit, specifically the licensing process and regulations and regulatory rules. Just a couple reminders before we really get going that we are recording this and we will be sending this out to everyone who registered afterwards, probably tomorrow, midday. We're also going to be posting it on the River Management Society YouTube channel, so you can always go there and check it out. We have a whole playlist on hydropower, so you can see some other relevant videos there as well. We're going to be using the chat today. So if you have any questions, feel free to type them in before you forget them. And then at the end of the presentation, we're going to have quite a bit of time for some Q&A. During that time, we might also be possible for you to raise your hand using the reactions button here on your Zoom bar. And you can then come off mute when called upon if you have something that's just hard to type in the chat or you'd like to further explain your question. And then lastly, we do have some closed captioning available. So you can direct your way to your Zoom bar and find closed captioning button if that is helpful for you. So without further ado, I'm going to go ahead and pass it over to our presenters today, Kevin Lewis and Dave Steindorf, and invite them to introduce themselves. And while they're doing that, we'd also love to know who's joining us today. So feel free to introduce yourselves in the chat box. So go ahead, Kevin.
Oh, good morning. And thanks for taking the time to attend this presentation. My name is Kevin Lewis, and then I'll let Dave Steindorf talk for himself a little bit, but not too much. I think just kind of to start off, Dave and I met back in 1997 on a hydropower project that we started working on together. So between the two of us, we have about 56 years of combined experience with hydropower licensing. So we've been around the block a lot. I think that's good enough for me. Dave, how about you?
Yeah, I guess the only other thing I'd add, walking into that room 25 years ago or whatever it was, Kevin owned an auto shop and was working as an auto mechanic. I was a high school teacher, so we didn't know anything then either. So it's yeah, it's an interesting world and it has its own language, and it's super intimidating when you first start doing this stuff. So I think part of the goal here is to help people to have maybe a little bit less of a painful process than what we had going through it, and try to share some of that and make sense of how these projects work and and understand some of the terminology.
Yeah, we would have killed for this kind of information back in those days. So anyway, so with that, let's move forward, because we have a lot of information over the next hour, and we're going to try and cover everything. And like Angie said, we have a half an hour allocated for Q&A afterwards. And if people are still asking questions, I'll stay longer and keep answering questions as best I can. So this is just kind of what was in the description of this presentation. Once again, a lot of information, and so we kind of got to stay out of the weeds as much as possible. And Dave will be my minder to keep me out of the weeds.
Hope everybody brought a lawnmower, but yeah.
So I think the one point to make here is that, you know, hydropower licensing is complicated. If you're involved in licensing now, you've already realized it's complicated. And the other thing I would say is that really, because of the nature of location and desired outcomes, every hydropower project is unique in many fashions. So there's like no cookie cutter hydropower project. They're all different, and understanding them is important. So I think first off, what is hydropower? You know, it's basically converting the energy of falling water into electricity. And you really need two components to generate hydropower. You need a vertical distance, which is called head, and a volume of water, which we'll call flow. And let's see. And I think the basic thing is the amount of power produced by a project is a product of head and volume. And so the higher the head, the less water is necessary to generate an equivalent amount of power. And so that's kind of what the trade-off always is in a project is how high do you build your dam, you know, or things like that. And the other thing is as much as I hate a slide full of data, I'm giving you a slide full of data, because you're going to hear these terms. I mean, what we always hear is megawatts, megawatts, megawatts. And so what's a watt? And simply put, a watt is a measurement of energy. And the analogy I use a lot of times is I compare this to a river flowing by your backyard. And voltage, like the wall socket of your house, is 120 volts. Voltage is really the pressure. So if it was a river, it'd be the speed of the current going by. And amperage is the volume of going by. So in a river, that'd be cubic feet per second. You multiply one by the other, and that gives you watts. And so it's just a way of measuring power. In hydro projects, we talk about kilowatts, which is 1,000 watts. We talk about megawatts, which is 1,000,000 watts. We even talk about gigawatts. I prefer to stay in megawatts, but you'll see gigawatts, which is basically 1,000,000,000 watts. If you generate that power or use that power for an hour, it becomes a kilowatt hour or a megawatt hour. Pretty simple stuff. And then finally, there's a definition that the federal government uses, mostly the Bureau of Reclamation and Corps of Engineers. It's called an average megawatts, which is basically a megawatt that's delivered 24/7 for an entire year. So it's 8,760 hours. And that's called an average megawatt. I've only seen that in federal projects, so you can pretty much just ignore that one and work in megawatts. And so we're going to kind of go through a lot of the different components of a typical project. And we're going to start with, obviously, dams. And I think the thing on the three dams on the left, to kind of give a good depiction of different types of dams. You have arch dams, gravity dams, then you have what's called buttress dams. And what a dam has to do is a dam has to exceed the force of the water pressing against it from the reservoir. So a gravity dam stays in place simply because it's heavier than the water in the reservoir that's pushing against it. An arch dam takes that pressure and compresses it in an arch form and spreads it out into the walls of the canyon. And so that's how it maintains that pressure. Then a buttress dam is kind of a cross between a gravity dam, except it's kind of smaller in volume, and it uses these buttresses on the back to also help resist that force. Buttress dams are pretty much older designs. You'll see them in old projects that were built back in the 20s and 30s, but generally it'll be a gravity dam or an arch dam. And I think the other thing you have is you have earthfill dams, which are gravity dams. Same thing, that the rock and soil and core of an earth dam has to weigh more than the pressure from the water behind the dam. Otherwise, bad things happen. Earthfill dams are compacted. Generally, the central core is clay, or it can even be concrete. But it's something that's got to be obviously impervious to water, because you know, if you make a mistake when you build a dam, bad things happen. This is kind of a cross section of a generic hydropower project. You've got a reservoir, and you've got a penstock, you've got a turbine, which is connected to a generator, then you have transformers and power lines. This is what I kind of call a storage project, and we'll talk about the differences later on. A variant of a storage project would be, instead of having the powerhouse at the bottom of the dam, in the dam, or very close to the dam, you move that powerhouse miles downstream, and you divert the water from the reservoir through tunnels, pipelines, canals, whatever, and take them down. You basically increase your head because of the gradient of the river. I call that a bypass reach, and because you've basically taken the water out of the river, moved it through the mountains down to a powerhouse, and then put it back in the river. Both projects can have their own environmental impacts. A storage project, you can have flows that jump up and down at high rates at times, which can be injurious to fisheries and aquatic life. A bypass reach, well, clearly, if you dewater the river, it's also impactful. So both kinds of projects can have their own impacts, but pretty much that's what you see is it's either going to be what I call a storage project, or it's going to be a bypass project. The other type of project is what we call pump storage projects, and that basically is a project that you build an upper reservoir and you pump water up to the reservoir, and then you generate with that water from the reservoir, and it goes up and down, up and down, and up and down. You have an open loop project where you might be located on a reservoir or even a river, a flowing river. Then you have a closed loop project, and these projects, I've seen proposals for these projects that are 100 miles from the nearest river, and they basically just use the difference in elevation, sometimes well over 1,000 feet from the upper reservoir down to the lower reservoir. I think and what makes these projects work is in periods of high demand, you also have high prices for power. And so when you have high demand, you generate, and when the demand goes back down, the wholesale price of power goes down, then you use that power to pump the water back uphill. So a pump storage project acts more as a battery than a typical hydropower project, because it doesn't really produce new energy. It stores energy, but it takes more energy to pump the water uphill than you get when you run it back downhill through the generator. So in essence, a pump storage project is a net consumer of energy. And that's something that's good to keep in mind, because somewhere else in the system, you have to make up for that extra energy to pump that water back uphill. But it is a way to meet some needs. And these days, they seem to be kind of the glowing new example of hydropower we need in the U.S. Although I think Dave would agree that we see a lot of proposals for pump storage projects, but very few ever get built because they're extremely expensive. And they're large. I mean, it could be 1,000, 2,000 megawatt projects. They can cost several $billions to build over 10 years or so. So pump storage is kind of the darling child right now, but once again, we're not seeing a lot of them built. So with that, let's look at a few dams. This is Shasta Dam in Northern California. It's California's largest storage project. It's a federal dam. It was built to provide irrigation, flood control, and hydropower as kind of a side benefit. 4.5 million acre feet of storage, so it is the largest storage reservoir in California. 330 feet ahead, and nameplate capacity of 663 megawatts. And just to define nameplate capacity is what the turbines can produce at maximum output. So that's the nameplate capacity. We'll talk about this a bit more in the future. But another view of Shasta Dam, and those 5 Pentstocks down to the powerhouse are large enough to drive a school bus through. So these kind of projects are huge in scale. Shasta Dam is actually a combination arch gravity dam. So if the arch should fail, the weight of the dam would keep it in place. I'm not sure why they needed to build a dam that met both purposes, but they did. Oops, sorry. This is Grand Coulee Dam up on the Columbia River up in eastern Washington. It's huge. It's got 550 feet ahead. It's a mile across the crest of this dam. And its nameplate capacity is 6,809 megawatts. So it's many Shasta dams can be generated here. And you can see the roadway along the top, and below the roadway, all those gates are release gates. They're called drum gates. We'll show you an example of those later on, but it's just the whole top of the dam is these giant drum gates. In high water events, this dam can release hundreds of thousands of cubic feet per second. Closer to Dave's home, this is Oroville Dam, which is the tallest dam in the United States. It's earth-filled dam. It's got a concrete core, 615 feet ahead, and a nameplate capacity of 819 megawatts. So it's a pretty good sized powerhouse in itself. The powerhouse is actually underground in this project. And then finally, in my backyard up here in Idaho, this is the first dam built on the Snake River called Swan Falls, and built in 1901 with 107 feet ahead and whopping nameplate capacity of 27 megawatts. That whole center section is the original powerhouse, which is now a museum. And to the left of it is the new powerhouse built back in 1990. Quite frankly, I'm not sure why this dam even still exists at 27 megawatts, but there it is. The problem with this dam is it was originally built with a fish ladder, which didn't work. They just abandoned it. And this was the end of salmon migration to all of southern and eastern Idaho to this day. So moving on to control structures, sometimes you got to get water out of dams, and there's a number of different ways to do it. This is what we call a vertical lift gate. Basically, it just uses a mechanism to lift this gate up and allow water to spill from underneath. Very common type of gate on a dam. Also common are radial / Tainer gates, which pivot and move up. They're a bit more complicated, a bit more prone to failure, but still very, very popular. And then the third type of release gate is what's called a drum gate, which is even less common. The federal projects like Grand Coulee and Shasta Dam use drum gates. Probably the thing about drum gates is they're fairly simple. They just have 2 valves, and that right-hand green valve, you close that valve and water flows into that drum gate chamber underneath, and the gate basically floats up. And those drum gates can be huge. This dam here on the Feather River, It's about 100-foot high dam. And those drum gates are 30 feet tall and 125 feet across, I think. One of the problems with them is you really don't have any control on drum gates. So they're open or they're closed. So if you have a high water event that you can't deal with, you basically drop the drum gates and walk away. And after the event's over with, you close the valve and raise them back up again. The dam in this photo is actually releasing water through a smaller radial gate, and that's for a whitewater boating release. Let's see. And this actually this project is a diversion project. The water in this project goes through a tunnel and goes downstream for 8 miles before it drops down through the powerhouse. And finally, really basic is what's called a glory hole. And it's basically non-mechanized. There's no control mechanisms to release water. When the water reaches the top of the glory hole, it just starts spilling over the edge and out downstream. So there's really nothing to go wrong with it. There's no mechanism to break. Power failure doesn't affect your release. I think the downside is when a reservoir gets high enough that it starts spilling the glory hole, there's not a whole lot you can do if you're a manager. And the image on the left is Whiskeytown Lake in Northern California. And in 1997, I saw 10 vertical feet of water going into this glory hole. The inflow into this reservoir was just huge. And it's got an earth-filled dam. And you never want to spill water over an earth-filled dam. And, you know, 1 or 2 more atmospheric rivers at that time could have been disastrous. So while glory holes are fairly inexpensive and they're not mechanized, the problem is they don't start working until the reservoir is full. And in this day and age of climate change and huge flow events, I'm not sure this is the best kind of a structure to rely upon. So moving on a bit, let's talk about turbines. This was actually the first modern hydropower turbine invented in 1849. There's really 2 turbines that you'll see in a project description: the Francis turbine, and the next one I'll show you the Kaplan turbine. This turbine can operate medium to high head. The little green things you see in the image are called wicket gates, and that's what actually allows water into the turbine. So the circular area is what the penstock is connected to, so it's pressurized from the reservoir. And you open the wicket gates, the water flows through the turbine, it starts to spin, and magic starts to happen. These actually work vertically or horizontally, so different designs for different projects. Let's see. And I think we jump down to, so Kaplan turbine was invented in 1919, it's just a bit later. It just basically took the earlier design and modified it a bit. And instead of having a fixed turbine, it now has adjustable blades on it. And so it can operate over a much wider range of flows. It's good for low head operations, like less than 200 feet for vertical feet. And once again, so Kaplan turbines and Francis turbines are really pretty much what you see when you read about a hydro project. There's a lot of different variations, especially like of the Kaplan turbine with adjustable blades. There's horizontal versions, there's bulb turbines, there's a lot of different designs, but Kaplan, Francis are the ones you really see. And I think the third is called a Pelton wheel, which are very efficient types of turbines. They can be used in really high head applications, but they are high speed, and so you have to reduce that speed down through gearing to allow them to work. But basically, they just shoot a jet of water into these cups, and just the design makes it very efficient. you see a lot of Pelton wheels on small hydro projects, even like ranches out in the backcountry. They'll run a 2-inch hose a couple 100 feet down a hillside and spin a little Pelton wheel and power the ranch with it. So there are Pelton wheels out there, but they're pretty rare. Generally, it's the earlier 2-type turbines. So moving on. So now we have what the turbine is connected to, the generator. And generator is basically where you generate electricity. And on the left side, there's like 2 components. There's a rotor and a stator. Probably step back. So you generate electricity by basically moving a magnet next to a conductor, which is a wire, copper wire. And that magnetism pushes the electrons in the wire, which is actually what electricity is, the movement of electrons. And so a generator, you basically create a giant spinning electromagnet that generates the electricity. So the rotor, which is spinning from the turbine, is energized with power and becomes an electromagnet. And the stator, which is all these windings. So on the right-hand image, the lower section is the stator, the section that's being lifted up is the rotor. But you've got miles and miles of wire in there wound. And but that spinning magnetic force is what actually generates electricity. And turbines generally generate something like 11,000 volts of electricity. They're huge. This rotor they're lifting out of here is 250 tons. So that's 500,000 pounds just in that rotor. So I mean, these projects are huge, and you can kind of tell by the left-hand image, the little icon of the person down there. And if you've ever visited, like, I think this is Hoover Dam, the powerhouse in Hoover Dam, these things are huge. They're pretty awesome to visit. I mean, the noise is tremendous. The smell of ozone in the air is powerful. It's pretty much a sight to behold. And so if you ever get a chance to take a tour of a big powerhouse like it's a Glen Canyon Dam or Hoover Dam, or even Shasta Dam in California, it's pretty impressive.
And I was just gonna chime in, Kevin, that one thing that's interesting, and I was astounded to learn this a while back, is that for the grid to operate effectively, it actually needs a certain amount of just rotating mass out there. So the weight that Kevin was just talking about is actually important for the grid to be able to function, because if there's a sudden load, like everybody turns on their air conditioners all at once or something like that, you need that moving inertia, going back to Kevin's original analogy, to keep the electrons moving through the system. And it's harder to get that out of other energy sources like solar or wind that just don't have the actual mass out there that's spinning around, which is a weird thing to think about. You know, if you're not used to like thinking about electricity, it's just, you know, it comes out of the wire in your wall. But anyway, it's important to note that mass actually does provide an important function for keeping the grid reliable.
Absolutely. And we'll talk about the grid later on, but Dave's totally correct. That's an important component. And then once you generate hydropower, what are you going to do with it? So generally outside the powerhouse, there'll be a transformer for each unit, each generator. And transformers are devices that either boost voltage up or drop voltage back down. And the reason for that is lower voltages have more loss in transmission. It's basically friction through the wires. And so you boost the voltage up. So like you get 11,000 volts out of the generator, it goes outside to this transformer. And you use a series of transformers to get the voltage up to a transmission level. Ultimately, Transmission voltages are anywhere from 69,000 volts to 765,000 volts. Actually, some are close to 1,000,000 volts these days. But that's what you need to move energy long distances and minimize the loss. There's always loss. I have a fairly high voltage line behind my house here, and when it's kind of foggy at night or in the wintertime when it's snowing, you can hear this crackling sound from the power lines, and it's actually voltage going to ground through the atmosphere and ionizing the air as it does it. That's what the sizzling sound is. And so there's loss from these power lines all through the process. You just have to make up for it. Let's see. So actually, we're making pretty good time here. So please excuse the coal-fired power plant on the left. just add a hydro plant there. But basically, this is how transmission works, distribution works. You've got power plants, you've got transformers that step up the voltage for transmission. On the other end, you have transformers that step the voltage back down and down and down until it gets to your house. And at your house, you basically have 220 volt circuits of power to use in your house. Fairly simple, but very complicated itself. The other thing we can talk about kind of how projects operate. So you'll hear the phrase run a river, and run a river is basically a project that usually does not have any storage capacity or has very limited storage capacity. And everything that comes into that project has to go out at this, basically at the same time. So it goes out to the powerhouse. So with run of river, you lose flexibility. A storage project where you can hold water and then release water and generate power when power is more needed. Obviously, it has a higher value when it's in demand, and so you can more maximize your profits. A run of river project, if you have to generate, there's times when the wholesale power price goes negative, and you may be generating power and actually paying people to take your power. So there's pluses and minuses on different kinds of projects. Load following, we also call peaking power, which is a project that basically follows the demand of the system. So as the demand increases, the price goes up, you increase your generation, you make more money. Demand drops off and you reduce your generation. So that's called load following. And if you look at the hydrograph of some projects that load follow, you'll see big fluctuations in like output from the project. So if there's a flow gauge below a dam that load follows, there was a project in Northern California on the Pitt River, Pitt number 1, and I used to look at the gauge, and it looked like a yo-yo all day long. That thing jumped up and down just continuously. They modified their output to kind of chase the dollar, basically, in generation. That kind of load following can certainly have impacts to the ecosystem of a river. And Dave, correct me if I'm wrong, but those projects are kind of operated differently these days. I mean, you have less of those radical fluctuations. And what do you think?
Well, and one of the big things that happened in relicensing was a big increase in the base flow level of the amount of water that had to be there 24/7. And so they were still allowed to peak on top of that, but you weren't going all the way down essentially to zero and then back up to whatever those other flows were. And just actually, I want to loop back up for just a second. There's my own personal bias. I don't like the term run of the river because it's usually not very descriptive. People think that means that you have a natural flow regime below a project. that's quite often not the case. It often just means that they're delivering downstream of a project whatever they get into their project, and whatever the input flow is above them may not be resemble a natural flow regime. You also hear things called like run of release, which is an invented term that just means that they're running whatever, let's say it's an Army Corps dam, whatever the Corps tells them to release, that's what they do. So you need to look at some of these terms and see what the actual release patterns are on projects, and not assume that because it has a certain name, it has certain characteristics.
Yeah, I don't disagree. And like I say, every project is different. Some, you can have a project with multiple uses. So like Shasta Dam, it's authorized in legislation was irrigation and flood control, and power generation's added to it to help pay for the project. There's a lot of projects where, state water rights dictate how water is released, when water is released. And if you have a hydro plant in that dam, you're constrained by water rights holders. So there are always a lot of variables, and when you're working on a project, understanding the playing field out there on how the project is operated, and how it's what all the different variables might be. Bypass reach we talked about a little bit earlier, and basically, it's you divert water out of a river and send it downstream through different conveyances and drop it back in the river. You create a bypass reach, and that earlier photo I showed you of the Rock Creek Dam on the North Fork of the Feather, when we started the relicensing on that project, the minimum stream flow from that dam was 0. And the dam just downstream was 50 CFS. Post-licensing, post-settlement agreement, post-licensing, now there's 300 or 400 CFS as an in-stream flow. So that's the improvement that was made through relicensing. But prior to that, as far as the powers that be were concerned, they were perfectly fine with a dry riverbed, basically receiving some leakage from the dam and some spring flow. So, and that's not uncommon here in Idaho. In Idaho law, a 0 CFS minimum flow is legal in this state, and there are rivers that have minimum flows of 0, and that parts of the year they're completely dry because they're either diverted for irrigation or hydropower. And then finally, I think the other reach we haven't talked about yet is what we call stair-stepped hydro, and we actually have a couple of examples of this. So this is the Upper American River Project. This is in, I think, one of Dave's projects, right? So the upper part of this diagram is kind of a cross section of the vertical drop of this project, and the little blue represents I guess the storage capacity of those upper reservoirs. But once you drop through like that third reservoir, from that point down, you're pretty much, quote, run a river. As the water comes downhill, it just keeps having to go through the powerhouses all the way down. And this is what we call stair-stepped hydro. And then the other one would be the North Fork Feather, which, your main water supply is Lake Almanor and the Mountain Meadows Reservoir sometimes when there's water in it. But once you leave Lake Almanor, you have just 2, 3, 4, 5 bypass reaches. And Dave, you could probably clarify this, but what were the minimum stream flows in those reaches pre-relicensing? They were all pretty
Yeah,
dry,
like
I think.
50 CFS, I think, below the Crested Dam, and 100 below Rock Creek. And this is in a system that unimpaired flows, in the summer, rock bottom would have been about 1,000. And California's, we're all kind of defined by our geography. California is somewhat unique in that you go from the crest of the Sierras all the way down to the valley floor in about 60 miles or so. So it's ideal for setting up hydropower projects. And both these projects, the SMUD project, and this is what PG&E calls their stairway of power. They essentially can run the entire river in a pipe from the crest up there, in this case up at Lake Almanor, all the way down to the valley floor and into Lake Oroville, and not have any water touch the river, or very little. So even though it's broken up into different segments, it just goes out of a pipe into a reservoir down to the next powerhouse and then on. But that's how they work.
And this brings us to the grid. So, what is the grid? Electricity flows through the grid. I mean, this is what's called basically the national grid. In this case, it's depicted as a western section and an eastern section. And as usual, Texas is a little special. Texas didn't want to be controlled or regulated by the federal government, so they created their own independent grid, which is not connected to the rest of the country. And so, as they discovered a few years ago when they had a super cold snap in Texas, what happens in Texas stays in Texas. They lost power, and the rest of the country had power. The grid's actually broken into about 8 subsegments, and it's got something like, the grid is not owned by the federal government. So you have multiple owners. I think you have something like 50 or 58 different entities that operate parts of the grid. Yet they all have to operate together. The orange lines on this image are proposed new lines and new interconnects. So they don't exist right now. Actually, the one over here is across southern Idaho, is being built right now by Idaho Power. It's called the Boardman to Hemingway. So it goes from Boardman on the Columbia River over to kind of central southern Idaho, and it's going to tie into. Then it's going to extend further. Actually, it's going to tie into a line that's being built from Wyoming down to California to bring a bunch of wind energy from Wyoming. But so there are parts of this orange are being constructed right now. Other parts may never be constructed, but this is just the general grid, which is about 125,000 miles of transmission lines. And then when you look at taking power from the grid at every town or small location and going through, different delivery systems to ultimately get to houses, at the end of the day, we've got probably millions of miles of wires strung around this country to deliver power. And this grid has to operate, with very, very tight tolerances, like Dave was saying earlier. That rotational mass from those big generators. If you look at so we use alternating current, what's called AC power, and you also have what's called direct current. In fact, some of these lines you see, there's actually some direct current here. Direct current is basically electrons flowing from point A to point B. The downside of direct current is you have huge losses in transmission, and it really isn't very efficient. Alternating current was actually discovered by a gentleman named Tesla. He worked for Thomas Edison for a while before they split the split company, because Edison was a proponent of direct current and Tesla was a proponent of alternating current, and they ended up in this huge fight. Ultimately, I think Edison had a horse electrocuted with alternating current to prove that it was too dangerous to use. But anyway, so alternating current is not a direct flow of electrons like DC current is. Alternating current flows back and forth, and it flows back and forth 60 times a second. So it's called cycles. So you see 120 volts, 60 cycles. That's what the cycles mean. So that the energy is actually flowing in 2 directions 60 times a second. And the entire grid has to operate in sync at a voltage level and that's 60 cycles. And if you deviate like one cycle, if you get out of sync like one cycle, you start having cascading failures throughout the grid. And so, and this can happen in milliseconds. And so it's all computer controlled. The regulation is, things happen faster than a human can react. So it's, you know, it's extremely complicated, and it's probably not going to get any less complicated. So going back to what Dave was talking about, rotational mass and turbines, that is really important to maintain the frequency of the grid. You know, you keep hearing in the news about we need to have a more modern grid, you know, and it's true. You know, we had more centralized generation when we had big coal-fired plants and big nukes. Those things are all going away, and we're going to more decentralized generation. I drove back from Death Valley a couple of days ago back to Idaho, and you know, I saw like 4 different solar projects out in the middle of Nevada in different places. And so same thing in Eastern Oregon. You'll find solar projects in the middle of nowhere. And so we have a more decentralized system of generation now. Same thing with wind and solar, and that's not a bad thing. It's actually, I think it's a good thing. But we do need probably a more modern grid. It is weird that you have, you know, that many owners of something that's so important to an entire nation or civilization. I mean, if it wasn't for electricity, we'd still be huddled around campfires cooking pieces of meat, you know, on a stick. Electricity is what made our civilization what it is today. So anyway, so that's kind of the grid part of it, and we're actually making really good time. So plenty of time for Q&A. And I think finally, I just jotted down some points to look for in licensing to think about if you're looking at a project. One of them is, and this gets back to nameplate capacity. How much power does the project actually produce? So say you have a 40 megawatt project. Does it produce 40 megawatts 24/7? And I would argue no, it doesn't. I did a lot of research here in the Pacific Northwest and looking at lower Snake River dams, looking at Hell's Canyon complex on the Snake River. I discovered that these projects only produce about 1/3 of nameplate capacity annually, and that's consistent over almost 20 years. And the reason why is water. You know, a good part of the year you don't have enough water to run all your turbines at full output. So figuring out what your project actually produces is important, because you know some people may make claims that aren't supported by reality. I think the second bullet point is, does the project have operational flexibility to meet changing needs? You know, hydro projects are operated today often much different than they were operated 20, 25 years ago. Especially in California with the amount of solar they have now. And even here in Idaho, Hell's Canyon is a very popular whitewater resource. It's below the Hell's Canyon complex. And with the advent of all the solar coming online, even here in Idaho, Idaho Power now generates more electricity at night than they do during the day. And so when people stop rafting and kayaking and make camp, the river actually comes up overnight and then goes back down the next morning. And the users are like, where's our water at? And Idaho Power is like, we don't need to generate during the day. We have plenty of power from wind and solar, and we generate at night now. Same takes place in California in the Tuolumne, and I suspect other rivers as well. And I think so operational flexibility is critical. And then the third one is, are there issues that will require mitigation? So to me, those are kind of like, I mean, I'm sure there's a million more bullet points a person could put out. And Dave, you're welcome to add in you might think of, but that was my first cut on it.
Yeah, well, when we do the talk next week, we'll talk quite a bit about how the power markets have changed and the importance of flexibility and really the diminished value of what are called base load generating facilities that just produce a constant amount of electricity. So the metrics that we've used to measure power in the past don't really make sense in our current grid, and certainly not in the future world out there.
Yeah, so actually we're about 10 minutes early. That's pretty good. So one thing before we go to Q&A, Angie is going to put a link in the chat. There's a little Excel spreadsheet that I developed many years ago when I was trying to figure out what it actually costs to do a whitewater release for recreation, because the utility was telling us it was $30,000 a day, and we didn't really accept that. And so built a little spreadsheet, and you all are free to download it and use it as you want. The red cells are the things you can change that won't break anything. I think, and I have notes off to the side of different projects I've looked at, but you can use this to calculate acre feet of water from CFS. You can use it to calculate the value of a single CFS of water going through a certain hydropower project. So it's very flexible. And Angie's going to stick it, I think, in the chat. So I think with that, I think we're ready to go to questions.
Actually, Kevin, before we move on, can I steal the screen here for a second?
Sure.
Have an example to kind of that's current with everybody about the differences between projects. Let's see if I can, wait a minute, where's my screen share option? Here it is. Let's see if I can do this. All right. Can everybody see that?
Yep.
Yep.
So Klamath dams are definitely in the news these days, being removed. And, one of the, common refrains from people that are opposed to the removal of those dams, like, well, we're going to lose all this power. How are we possibly going to make that up? We're losing all this clean, renewable energy. So, 5 dams on the Klamath, their dependable capacity, going to the point of, Kevin, the difference between rated capacity, what's theoretically possible, and what they actually produce. What they actually produce is around 75 megawatts per year. So 5 dams, and then you have to look at the cost of that, which has been, the kind of the destruction of the 3rd largest salmon run on the West Coast, water quality issues, etc. But 5 dams to produce that much power. Right out my back door, little tiny powerhouse here, Bucks Creek Powerhouse up in the Feather River Canyon, has a throughput of a whopping 400 CFS, produces more power than all 5 of the Klamath dams combined. So that gives you an idea of the differences between different projects and what their actual energy capacity is. And the reason for that difference is the Bucks Creek Powerhouse, built clear back in, I think this is like 1924, has almost 2,000 feet of head. So 2,000 feet of drop. The pressure coming out of the bottom of the Pentstocks there is about a 1,000 PSI. So you simply get a whole lot more bang for the buck with this powerhouse, which is also completely flexible given its configuration. So projects are different. They have different impacts, and they also have huge differences in the amount of power and the type of power that they can create. So that just seemed like a good example that's kind of current in the news. So I guess we'll go to questions.
With that, yeah.
Yeah, and we've had some questions come in through the chat. Let's see here. One of the first ones that came in was when we were talking about pump storage, and Kristen asked, is it always the case that pump storage projects use more energy to move water uphill than they produce when the water moves back downhill?
Yes.
I think Isaac Newton figured that one out a long time ago. It's called conservation of energy. You can't use the energy and then somehow get more out of it than what you put in. But that said, the grid realities to make that type of storage viable and important. I mean, I've just been watching while we've been talking today, power prices here in California on the wholesale level have gone from about $30 a megawatt hour, and now it's at $5.15 a megawatt hour, and probably here in another hour, it's going to be negative. So in the current reality here in California, they could actually get paid to pump that water back uphill, which is why they're looking at those projects, notwithstanding the other issues, environmental impacts, and also these projects are just really expensive. I mean, it's probably $1 billion to put in a pump storage project, but the market realities out there do make them viable, theoretically.
It takes 20 to 25% more energy to pump the water uphill than you get when you generate going downhill. So the efficiency is marginal. And when you look at different power sources, I mean, if you look at batteries, like Tesla batteries, giant battery packs, they're, in the 90 percentile efficient, and their response time is in milliseconds as opposed to the time it takes to convert from a generator to a pump and back and forth. So there are a lot of differences, but it certainly seems to me like, and pump storage has been around for like almost 100 years. It's not a new technology, but it's newly discovered by some, I guess. I mean, my congressman talks a lot about pump storage, and he also talks about small modular reactors too. And what can I say?
So I saw another question come in from Nina asking a clarifying question. Run of river means that whatever water comes to the dam is what is released from the dam, aka no holding. But there could be holding upstream or downstream, which means it's not the natural flow of the river.
Yes.
Yes.
Is why I don't like that term. I mean, it doesn't, you have to look at the hydrology. I mean, theoretically, those cascading projects that we showed, where it basically you can run the entire river in a pipe from the crest of the Sierras all the way down to the valley floor. Those could be called run of river projects because each of those little forebays, they're not very big. They don't store water. And I've seen projects like that where people actually, several years ago, there was a push to import power from British Columbia to California to meet our renewable energy objectives here. And the proponents of those projects were calling them run-of-river projects, even though they had these massive bypass reaches. So anyway, the short answer there is just because somebody slaps that name on a project, you need to look at the actual hydrology of the project to see how it's operated.
Yeah, I agree. I saw a comment jump up on the screen. It says, do waterfowl ever go down a glory hole? Yes. I actually saw a story about a duck that went down the glory hole that I showed the photo of, and it survived. It came out the other end. Unfortunately, the person that swam out to that glory hole didn't.
Wow.
Yeah. So at least one person took the ride.
When you were showing that awesome map of the grid that had of the United States, someone asked, is it online? That map of the grid.
Oh yeah, I stole it right offline. Yeah,
Okay.
just Google images of grid and you can steal everything.
And then Jack asks, on areas of the grid where there isn't large hydropower, What other generation sources or grid assets provide the grid stabilization services that the spinning mass of hydro turbines provide?
Well, there's still, I mean, across the country, any of the fossil fuel plants, or what are called thermal plants, you're burning something to create steam, and then that spins a turbine. So it's just a difference of having water pushing that turbine, and then the generator, they actually heat water, create steam, and then that's what they use to spin those. So that's what's typically used. In terms of renewable resources, they do have it now where the like solar can provide some of that. But I think that there are, some issues of how well they can provide that type of reliability component. But I would say in most places where you don't have hydro, it's typically it's other thermal plants that are providing that.
Yeah, I think steam turbines, nukes are also run steam turbines, and they definitely provide some spinning mass. Not as much as those big giant hydropower turbines, obviously. Large industrial batteries. Originally they really weren't programmed to produce that kind of force, but it was just a matter of changing the parameters of the battery. And so these large batteries can also produce some of that grid regulation as well.
Yeah, and that thanks to Matt for the that interactive map he put in the chat. I mean, that really is interesting to look at, just to see how the different types of energy resources are distributed throughout the country. And I think Oak Ridge or NREL or somebody actually has a map that shows you how energy is moved across the grid over the course of a day from different regions of the country. If I can find that, I'll throw that up there. It's an interesting animation they put together.
And I saw a question from Sam ask, Kevin, you talked about rotational mass. Does that imply that we are dependent on hydropower to some degree, or i.e. can wind fill that void?
Every kind of generator has rotational mass. And so does 100 wind turbines provide the same rotational mass as a smaller hydro generator? I mean, it's hard to say, but I would say that the large federal dams that we have with these huge turbines, I mean, that's a lot of rotational mass. And I don't know that, I mean, if you're working on a hydropower license, generally the operator will say, this project is really important for grid regulation. They all say it. They all say it on every project. And in talking with engineers, they disagree that you can actually, the grid regulation can actually be done by fewer projects, and especially these big projects. So I don't think that we're going to be dependent. I mean, these big federal projects are going to be here longer than we're going to be alive. That's just a fact. I mean, Grand Coulee Dam is going nowhere. Yeah, I mean, it certainly does provide. I mean, the speed of the turbine is actually what sets the cycles. The 60 cycles that I talked about is actually derived by the speed of the turbine. It's how fast you're changing the magnetic field from positive and negative as the turbine is spinning. And so that's what's really important, is maintaining the speed of that turbine. And as the load increases, you have to open the wicket gates further to get more water through the turbine to maintain that same speed under the increased load. And so to me, it's a very complicated dance that occurs 24/7. I'm glad I'm not in charge of it.
And
I would fail miserably.
And at the risk of belaboring this point, hydro projects are as different as nuclear power is from wind. And you hear a lot of things out there about hydropower can do this, or hydropower can do that. it just depends on the project. You know, some projects just of their physical makeup are incapable of being flexible, and that flexibility is important for being able to integrate wind and solar into the grid. But some projects are just not because of regulation, but just because of their physical makeup. They have flumes for water conveyance systems, or they don't have forebays that are big enough that allow them to peak the project up and down. Or you need to have a re-regulation facility below them. So there are many different types, and trying to lump all hydropower into a single category is just a fool's errand.
So this one is a question from Doug. Doug asks, I work for a BLM field office with a couple FERC hydropower projects. My question has to do with NEPA. We had a power company with a proposed project that had the possibility of causing significant impact to resource values. FERC considered that action project maintenance, covered under the license, and did not do NEPA specific for that project. Is that typical?
So so it sounds like this is work that they were doing after, not during the relicensing process, but work to be done after a license was issued. Is that right, Doug?
That's correct.
Yeah, usually, I mean, if it's described within the license, that, I mean, the FERC does NEPA on these things, and it's usually considered to be included. But if it's something that wasn't described at all within the license, or it's you know, some kind of significant rearranging of the project, I don't think that would be included. What do you think, Kevin?
I would agree. I mean, if it's an action that exceeds the license itself, and the license itself went through NEPA, but if it's something that's outside of that, I mean, I'd hate to be the one to advise you to get a good attorney, but I don't know if one agency can sue another agency, but it sure seems to me like there should be some better analysis on something like that.
Okay.
Well,
Nina.
we've crashed the RMS website.
Well, I just tried going, so I did provide a link at the beginning to this hydropower licensing toolkit. That is the correct address, but right now it's looking like none of the RMS pages are working, and so we're gonna work on that and get back to you.
We're really sorry.
That is the correct address, so you can bookmark that and check that out. I did see a question come in. Nina says, I'm surprised and sad to hear that FERC said it's legally okay for a river to have 0 CFS, as Kevin noted in the bypass in Idaho. When did that happen, and how is there no protection of that river? Or what was the argument that said that's okay?
Actually, it's an issue of state water rights. So states own navigable waters and lands beneath navigable waters. So states control water rights. And in Idaho, we are a very ag intensive state. It goes way back to statehood. And the farmers run the legislature, and the farmers make the rules. And, if you had an ESA issue, there would be a chance to maybe have a way to get into that. But if you don't have an ESA issue, and it's just a matter of water management, that's kind of left up to the states. It would be tough. It would be a tough nut to crack. Having worked for an environmental group here in Idaho for 15 years and working on water quality issues, it's challenging when you work in an atmosphere that just doesn't really put that much concern on water quality and fish and wildlife species, and more concern on irrigation diversions.
Yeah, and I was surprised to find out looking back at some of the historical documents of the project where Kevin and I met up on the Feather, when that was first licensed back in 1948. I mean, I just kind of assumed that, it was the era of big dam building and that the agencies probably just vacated the field and PG&E got whatever they want. Actually, the Fish and Wildlife Service recommended a flow of, I think, 400 CFS below those dams. PG&E's opening offer was 0. And they ended up at 50, but it's just kind of the swing of the pendulum, where after we went through relicensing, we ended up with flows below those dams of 400 CFS. The problem was in the 50 years in between there, the river was virtually devastated. So if we'd gone with the recommendations from the resource agencies back in 1948, we would have continued to have probably have a robust fishery, recreational resource, all those things throughout that time period, rather than have it virtually destroyed and then bring it back 50 years later. So that's why we engage in the process and hopefully go out there and try to make things better.
I did see a comment from Colleen saying this is a great flow calculator tool. And if there's time and we're out of other questions, maybe we can walk through how and when and why to use the calculator. So throwing that out there, planting that seed. We do have a couple other comments. Sam said peaking reaches. Oh,
I was gonna say, Kevin and I were talking before the presentation about putting a README file in with the flow calculator to help with that. But yeah, because it's a little challenging just to walk into that and figure out how to use it. Go ahead. Sorry, Ed.
that's all right. And I think we might have some time to take a look at that here. But Sam said peaking reaches can be big impacts for recreationalists and aquatic species with hourly fluctuations. Hoping to get input on how to better comment in these operations.
Dave, you got 20-something projects under your belt.
Well, well, one of the challenges out there, and we're actually working on this right now, have a project with the Department of Energy to develop a tool just to better understand the value on the energy side of those projects. I'm not sure what, Sam, what your experience has been, but my experience has been that the economic analysis that FERC does is woefully inadequate. And one of the things on peaking reaches that we've advocated, that the Pitt River example that Kevin gave earlier, putting a substantial minimum in-stream flow has really improved that river resource below the project, and they're still able to peak it every day. It still has significant power value, but the fact that it's not going all the way down to 0 and then back up again makes a huge difference. But you need to have a tool to be able to evaluate the trade-off there on having, a peaking for a smaller part of the flow range of the powerhouse. So that's something on all of our projects that the hydropower industry likes to talk about, the value of the flexibility of projects, which can be true, but you can't evaluate it if you can't measure it. So I certainly recommend asking the utility to be able to provide some kind of analysis to demonstrate not only the existing value of the project, but how that value would be impacted if you recommend different types of flow scenarios. It could be changes on ramping rates. It could be changes on minimum in-stream flow. And then obviously you have to, directly impact what the impacts are to species, including people. Sometimes you get flow. I worked on a project where flow fluctuations were so severe, somebody was actually drowned on the project. And, that's clearly unacceptable. Hope that helped.
Right now, I don't see any other questions in the chat. I see some good comments. Matt provided a couple links about osmotic energy. And if anyone does have any questions, you're welcome to come off mute and ask, or you can put them in the chat and I'll read them out.
I've got the flow calculator queued up. I can share my screen and do a quick.
That'd be great.
Let's see if I can make this work. Okay, here we go. So, like I said,
All
the
right,
red
Kevin,
cells.
Kevin, can you blow up your screen a little bit?
Oh, sure. Get to the right spot here. Does this help at all?
Wrong way. Zoom in.
Let's see.
Just if you go to the bottom right, or yeah, where you are.
Oh, yeah. Okay.
Thank
How
you.
about this?
Perfect.
Much better.
Okay, so the red cells are the cells you can change if you want to play with this. And I basically inputted last night this figure. So I inputted the capacity of this powerhouse, which in this case is Rock Creek Powerhouse in the North Fork of the Feather. So it's 112 megawatts is their capacity. And that's at 2,880 cubic feet per second. So that's the two numbers you need. So what it gives you below that is how much generation is produced for every cubic foot per second going through the powerhouse, 100 cubic feet per second and 1,000 cubic feet per second. Then if you want to look, so you can basically, get a value of that power, because you can go down to just above the yellow cell and you can input the current power rate for any period of time. So in this case, I inputted $30 a megawatt hour. The bottom part of that block, actually, you can use to value a flow over a certain period of time. So in this case, I inputted 1,200 CFS, and what I subtracted was a minimum in-stream flow, which was already required. So it shouldn't be counted towards this like recreational flow. So that's the 450 CFS. I used a duration of 6 hours. So it tells you what the foregone generation is in megawatt hours, how many acre feet that is, the cost per acre foot, and then actually the cost of the release. So basically a 1,200 CFS release minus the 450 CFS in-stream flow for 6 hours at $30 a megawatt hour would cost $5,250. That's what it quote costs the utility to not be generating and releasing water for recreation. And this was really born out of the fact that when we were asking for boating flows back in before 2000, PG&E was telling us that a day of whitewater was $30,000, and Dave and I just didn't believe it. And but we really had to dig to find the information to help us refute that argument. Below there's a section just to convert flows into acre feet. If you ever want to measure the volume of water for different purposes. I use that in Idaho a lot because I worked on water rights. So in the rest of the spreadsheet, you can save information that you might need or whatever else, but that's kind of how it works.
And not to give away the punchline for next week's presentation, but as I predicted, while we've been talking, average power rate across California right now is negative $6.97 a megawatt hour. So under that theory, they should be paying us to provide recreational flows below the dam. So it just shows you how dynamic things are out there. So what that means in real terms, there's more electricity on the grid here in California than we can currently use, is why that price is negative. And renewables are providing 76% of the load out there. So 76% of the the energy supply in California is currently being met by wind and solar and other renewable resources.
And if you go online right now to any kind of a Facebook comments or whatever else about solar power or wind power, you will hear people claiming that California is racked with blackouts because of all their solar and wind. And sorry, that's just not true.
So I would imagine there might be some questions on the calculator tool there, or did people want to go play with it?
Yeah, Colleen, go ahead.
Yeah, thanks for running through it. That's helpful. Just given what you're just talking about with the price volatility, obviously that 6 hours that you put into the calculator, the price isn't the same for that 6 hour period, right? So
Right.
do you have a suggestion for where people could go to look for like average prices over a certain time frame?
Yeah, we'll cover that next week.
Okay. Just a teaser
well-
then, never mind.
Well, and it's further complicated, but it's different in different parts of the country. California, we're lucky that, I mean, it is literally this transparent. I can look online and see what not only average prices across the state, but in particular areas of California are. Other places are not quite that good, but the general trend is, we are seeing it across the country particularly with increased amounts of solar power, but we'll talk about that more in detail next week.
In contrast, my nearest trading hub is the Mid-Columbia hub. We call it Mid-C. It's over on the Columbia River. And to get access to the Mid-C prices and information requires thousands of dollars to subscribe to them. So it's basically unreachable by me. I mean, I used to get an email from the Bonneville Power Administration every month, and it would talk about the average wholesale power prices, and I would grab those numbers and stick them in a spreadsheet, but they stopped giving that information out about 1.5 years ago. And so I have some information. And same thing, I mean, there were times when the wholesale power rate was below $10 a megawatt hour. And the reality, I saw one comment pop up about nuclear power. In the world of power, the lowest price power is what gets sold the first. And if you've got a nuclear power plant that's churning out a couple thousand megawatts, but the cost is $100 a megawatt hour, you're not competitive. And my congressman is such a fan of small modular reactors because he's from Eastern Idaho, and we have a national laboratory over there that does research on small modular reactors. Well, they were going to build one, and they'd promised a power rate of $58 a megawatt hour, which is already not really competitive a lot of the time with wind and solar. And then they just doubled the number to $90-something a megawatt hour. Well, that project's gone now; it's on hold. So you've got to be competitive, and large thermal plants like coal. I mean, yes, they're going offline because of the environmental damage they do, but they're also just not competitive anymore. And what's competitive is wind and solar. I mean, you see solar projects in California with contracts going for $20 a megawatt hour with battery backup. You really can't beat that.
I just put the link to that price map if you want to look at that and nerd out on it for a while for California, so you can see what's going on.
I saw a quick question from Tracy about batteries at a hydro plant.
Yeah, I'll read it out just in case anyone's joining
Yeah,
by
please.
phone. Tracy asked, we have a licensee adding battery storage to their projects. Are adding batteries pumped storage? They've already been through relicensing. How could that fit into the FERC process?
In my opinion, they're better than pump storage because they're more efficient. and they respond quicker. If I had a hydro project, I'd stack a bunch of batteries up. And when the wholesale power price went down, I'd charge my batteries. When the price went up, I'd discharge my batteries. I'm not going to use it as a rationale to build a hydro project, but if I had a hydro project, I'd put batteries on it. And you don't have to do that. The batteries can be 50 miles away or 100 miles away. Just as long as you're tied into the grid. They don't even have to be at the project. They can be anywhere in the system.
And yeah, we're working with the Department of Energy and developing a tool to help figure this out, for both figure out the real value of, a hydropower project using hourly or sub-hourly pricing, but then a tool to figure out what would be an optimal battery size. And yeah, Tracy, I think there's a lot of interesting possibilities. I mean, you could size a battery just to allow you to back up like a particular part of a flow regime. So for instance, out here, foothill yellow-legged frogs have been listed, and we figured out that you need to have really slow ramping rates in order to protect those frogs. Well, that's probably going to require you to release water at times that's suboptimal for power generation. But if you were to back that up in a battery and then dispatch that optimally for the grid, there's a win-win there. So I think there's a lot of potential to do this, and different ways to size the batteries to do specific things for the hydropower project. So I think there's a lot of potential there.
Pauline's got her hand up.
Can I just jump in on that topic too? I just popped a link in the chat to a presentation from a couple years ago, but there is a difference between putting batteries in at a hydro project and linking the batteries with the hydro project for their operations. There are a lot of people who are interested in co-locating battery storage projects at hydro sites because there's already access to the transmission lines and the grid, but they aren't necessarily operated together. So just like different structures to think about.
Yeah,
and you might be able to, if you co-locate at a hydro plant, you're probably not incurring grid charges. If you're 50 miles away and putting power in the grid, that you're going to be paying somebody to move that power through the grid. I mean, you don't access the grid free in this world. There's no free lunch on the grid. So if you were at a hydro plant, you could take the power right to your batteries, and you haven't become part of the grid yet, and you kind of piggyback on the utility or whoever owns the hydro plants.
And the trick for those of us in the river conservation world is going to be getting that storage linked to a flow regime that we want to see there. They can just go do storage, right? Anytime, just to provide the needs for the grid. But the trick is linking that up with a flow regime that we all perceive to be beneficial. That's going to be an interesting discussion in relicensing and other projects to be able to put those two things in there, because they can just do it on their own. And the actual location of the batteries, as Kevin pointed out, doesn't really matter. But what's going to matter to us is that we get the flow regime that we want out the other end, and not have the grid needs be the stumbling block that keeps you from getting to that flow regime that you want to see.
Absolutely.
Well, this has been some great information shared, and I just want to say thanks again to Kevin and Dave for your presentation today. I know we're kind of coming up at the end of our time. If people do have any more questions, we can stay on and answer those. But I just want to remind folks that next week, same time, different link, we'll be continuing this conversation, and Dave and Kevin are going to go a little bit deeper into things. So if you haven't registered, please register, and we'll send you reminders and all that. I'm also going to be sending out a link to this recording and the slides probably tomorrow midday. So just thanks again for everyone joining, and I hope you have a great rest of your Wednesday, and we'll stick around. If anyone has
Thanks,
any-
everybody. Appreciate it.
Thank you.
Thank you. Bye-bye.
Bye.